Imagine you're managing a city's traffic grid, right?
Yep.
And it is just absolute gridlock.
Oh, and total nightmare.
Right. Cars are backed up for miles, horns blaring, nobody's moving anywhere. And your first instinct, I mean, the instinct of basically any urban planner, is to just bring in the bulldozers.
Yeah, build wider lanes, put up new overpasses.
Exactly. Just pour more asphalt,
Right.
which, costs billions and takes years. But, and this is what we're looking at today, what if an engineer walked in and just said, put away the bulldozers. I could fix this overnight using the exact same roads.
Just by, what, tweaking the system?
By fundamentally changing the timers on the red lights.
So welcome to the deep dive. Today we're talking about this really profound shift from a mindset of more to a mindset of better choreography.
It's such a beautiful concept, and it's so incredibly relevant right now because, well, we are seeing that exact same shift happen right at the bleeding edge of physics.
Right. Instead of solving a complex bottleneck with just, blunt force hardware, researchers are actually looking at how a smarter schedule can just eliminate the friction entirely.
But, I have to ask, does that logic actually apply to something as deeply complex and honestly resource-intensive as quantum computing?
You'd really think it wouldn't, right?
Yeah, because it feels like in that space, the only way forward is just building bigger and bigger hardware arrays.
Mm-hmm.
We're constantly hearing about companies needing millions of qubits just to make these machines actually work.
Right, that's the standard narrative. But there's this fascinating new paper out of Classiq Technologies by Gilad, Kishony, and Austin Fowler that really proves otherwise.
Oh, wow.
Yeah, they focused on quantum error correction. Specifically, they were looking at the system called the planar color code. And they essentially found a way to fix a fatal vulnerability in it without adding a single extra piece of hardware.
Okay, the planar color code. Before we get into how they fixed it, we probably need to understand the stakes here. Because, if you follow the race to build a useful quantum computer, you basically only hear about something called the surface code.
Yeah, surface code is everywhere.
Right. It seems like every major tech company is just betting the farm on that specific architecture. So why are we talking about the color code today?
Well, so the surface code is definitely the current heavy favorite for building a quantum computer on a flat 2D chip. It's solid, it's reliable.
Okay.
But the color code, which also uses that flat 2D layout, is essentially the more talented but maybe slightly more volatile sibling.
Huh. I like that.
Yeah, it has some massive theoretical advantages.
Yeah.
First off, it requires significantly fewer physical qubits to achieve the exact same level of error protection.
Oh, so it's just much more efficient right out of the gate.
Exactly. But the real magic is in the actual operations. The color code allows for something called transversal Clifford gates to be executed just much, much more easily.
Okay, stop right there. Transversal Clifford gates sounds incredibly intimidating.
Fair point, fair point.
What does that actually mean for the machine itself?
So think of transversality like a global software update.
Okay.
In a normal quantum system, if you want to perform a complex logical operation, you often have to painstakingly interact with the qubits one by one or in these messy groups. And that just introduces tons of noise.
Right, which is the enemy of quantum states.
Exactly. But a transversal gate allows you to apply that operation to every underlying physical qubit simultaneously. Clean, fast, totally in parallel.
Wow. Okay.
And the color code is just naturally built to allow this. Plus, it acts as this highly efficient refinery for something called magic state cultivation.
Okay, then another amazing term. Magic state cultivation. It sounds like we're brewing potions here, not building computers.
I know, it really does sound mystical. But it is purely practical. Just think of magic states as the high-octane, specialized fuel that you absolutely need to run the most complex quantum algorithms.
Like the ones that actually solve real-world problems.
Exactly. And the thing is, most quantum architectures are terrible at producing this fuel. They waste huge amounts of space and time trying to, distill it. But the color code, just by its geometric nature, can cultivate these magic states with incredible efficiency.
Okay, so leaner hardware, global updates, and high-octane fuel. It sounds like the ultimate quantum architecture.
On paper, yeah.
But obviously there's a catch, right?
Mm-hmm.
Otherwise, nobody would be using the surface code at all. So where does the color code fall apart?
The catch is all about how it handles its own internal errors. Because you have to remember, quantum states are incredibly fragile.
Right, like a stray photon or a temperature bump can just destroy the data.
Exactly. So to protect the information, these systems use what are called auxiliary qubits. Just extra qubits whose entire job is to constantly check the data qubits for errors.
Makes sense.
But there's a massive rule here. They have to check for errors without actually looking at the quantum data itself.
Wait, how do you check something without looking at it?
Because if they look at the data, the quantum state collapses, and your whole calculation is ruined. So this really delicate checking process, it's called syndrome extraction.
Right, indirect measurement. I think I've heard this described like trying to figure out if two coins in a totally dark room are showing the same face, both heads or both tails, without ever turning on the light to look at them.
Yes. That's a great analogy.
You send in a third auxiliary feeler coin that just bumps into them and comes back with the relationship data. It just tells you, yeah, they match, or no, they don't match, without ever revealing what the actual faces are.
That is exactly it. You extract the syndrome, the error footprint, without reading the actual data. Now, in the surface code, that feeler coin generally only has to bump into 4 data qubits.
Okay, pretty manageable.
But the color code is built on a honeycomb lattice. Its fundamental shape is a hexagon. So in the bulk of the system, a single auxiliary qubit has to check 6 data qubits at once.
Wow. Okay.
Yeah, this is known in the field as a weight 6 stabilizer.
So if the surface code is like your standard 4-way intersection, the color code's weight 6 stabilizers are like a massive 6-way roundabout.
Exactly. And just like a real 6-way roundabout, managing that traffic is really complicated. Because in the quantum circuit, that auxiliary qubit cannot physically check all 6 data qubits at the exact same instant.
Oh, it has to do it sequentially.
Yeah, it has to perform a sequence of 6 individual 2-qubit operations known as CNOT gates, one after the other.
And a sequence requires time. Like it's a chain of events.
Yes, and that time is exactly where the vulnerability lies, because if a random physical error happens during that sequence, say right after the 3rd gate, on the auxiliary qubit itself, that single error doesn't just sit there.
It spreads.
Exactly. It propagates through the remaining gates in the sequence. So a single random fault suddenly infects multiple data qubits before the checking cycle is even finished.
Yikes.
This specific cascading disaster is what we call a hook error.
Okay, let's unpack this, because I really want to understand what this does. What exactly does a hook error do to the system overall? Because, in quantum computing, errors are happening all the time anyway.
All right, constantly.
That's why we have error correction in the first place. So what makes this specific error so fatal to the color code?
To understand the damage, we really have to look at how errors travel across the physical chip. When an error occurs, it creates this anomaly in the lattice, an excitation.
Okay.
And because we're dealing with a color code, the hexagonal faces of this honeycomb lattice are mathematically assigned colors, specifically red, green, and blue.
Okay, color code makes sense.
So these error anomalies are called red, green, and blue enyons.
Enyons. It almost sounds like a particle.
You can basically think of them as the physical footprint of the error. Now, in a healthy, robust quantum system, if one of these enyons appears, it would have to travel a very, very long way to cause a problem.
Like across the whole chip?
Right, hopping from one adjacent qubit to another, all the way across the physical board to cause a true system failure, which we call a logical error. The minimum number of steps or faults it takes to create that fatal failure is called the system's circuit-level distance.
Okay, so the distance is essentially our defense shield.
Exactly.
A bigger distance means a stronger shield. We want those enyons to have to, hike a marathon to ruin our data, not just cross the street.
Precisely. You want to force the environment to produce this incredibly unlikely string of consecutive errors just to beat your system. But here is where the hook errors become catastrophic.
Do they make the hike shorter?
They act as deadly shortcuts. When a hook error happens midway through that 6-gate sequence we talked about, it typically spits out a correlated error on 2 separate data qubits simultaneously.
Wow.
Yeah, it creates a weight 2 data error.
So instead of the enyon taking one single step across the board, the error allows it to take 2 steps at once.
Exactly.
That doesn't sound ideal, obviously, but is it an absolute deal breaker?
It becomes a deal breaker because of how we used to design the schedules. See, in all previous research, when designers built the timing schedule for those 6 CNOT gates, they used the exact same sequence for every single hexagon across the entire system.
Wait, really? A totally uniform schedule?
It was a spatially uniform circuit.
Okay, let me guess. If every single hexagon has the exact same schedule, Then the shortcuts they create are identical too.
Yes, because every hexagon operates on the identical rhythm. Those wait-to shortcuts line up perfectly across the board.
Oh, I know.
They literally link together into a highway. And NEAM can ride these linked shortcuts all the way across the quantum chip in half the time.
That is wild.
So if your defense shield, your code distance, was supposed to be a 10, these uniform hook errors instantly drop it down to a 5. The shield is mathematically halved by your own internal schedule.
That is just brutal. So you build this beautiful, super efficient color code, and your own error checking mechanism basically cuts its defense in half. But wait, if researchers knew this was happening, why didn't they just, use more of those auxiliary feeler qubits, like have 2 of them per hexagon checking each other, so the error gets caught before it can even create a shortcut?
It's a great question, and honestly, researchers did try exactly that.
Oh, they did?
Yeah, there's this well-known design called the superdense circuit. It uses 2 auxiliary qubits per hexagon instead of just 1. And you're right, it successfully preserves the full defense shield. The distance doesn't drop at all.
Okay, problem solved, right.
Well, no, because by doing that, you fall right back into the trap we discussed at the very beginning of this deep dive.
Oh, we brought up the bulldozer.
Exactly. We brought out the bulldozers. The superdense circuit inflates the total qubit footprint drastically.
Right, because you're doubling the checking hardware everywhere.
Yeah. And the whole reason we wanted to use the color code in the first place was its incredible efficiency and low qubit count. If you have to double the checking qubits everywhere, you completely lose the primary advantage of the architecture.
Ah, I see.
So the holy grail of the color code is keeping that ultra-lean, single auxiliary per plaquette efficiency, but somehow maintaining the full, unhalved shield strength.
So we are completely stuck between a rock and a hard place. We either accept a halved defense shield, which makes the computer basically useless, or we bloat our hardware, which totally defeats the purpose of the design.
Right.
And here's where it gets really interesting, because Kishony and Fowler found a way to break that compromise entirely, and they did it by literally looking at the paint job.
Yes. What's fascinating here is their crucial observation about the geometry itself. So remember how we said the hexagonal faces of the honeycomb are assigned colors, red, green, and blue?
Yeah.
They noticed something remarkable about how those sit on the lattice. A hook error that acts as a deadly distance-having shortcut on a red hexagon. That exact same error sequence is actually completely harmless, totally benign, if it happens on a blue or green hexagon.
Wait, I need you to explain that. An error is an error, right? A flipped bit is a flipped bit. How can the color of a mathematical grid change the physical damage of the error?
It all comes down to the direction the ennies need to travel to actually cause a fatal logical error.
Okay.
To break the system, an ennian must create a continuous path that connects all 3 outer boundaries of the quantum chip.
Right.
Now, a specific hook error might create a shortcut that points exactly along that fatal path for a red ennian. It propels it forward toward the boundary.
Makes sense.
But for a blue ennian, that exact same shortcut is actually pointing sideways. Doesn't help the blue ennian cross the board at all. It's basically a shortcut straight into a brick wall.
Oh, it goes right back to the traffic grid analogy.
Yes.
The old way, that uniform circuit, was like setting every single traffic light in the entire city to follow the exact same 60-second timer, regardless of where they were. And obviously that causes gridlock, because a schedule that works perfectly for like a busy north-south avenue is going to be completely disastrous for a quiet east-west side street.
Precisely. A uniform schedule just completely ignores the local spatial context of the errors.
So instead of giving every single hexagon the exact same schedule, you customize the light timings. You tailor the operation order based on the specific angles and traffic flow of each unique color.
That is exactly the breakthrough. Kishony and Fowler completely abandoned the uniform schedule. They assigned a totally distinct CNOT sequence to each of the 3 colors.
Oh, wow.
Yeah, so the red hexagons get one specific 6-step schedule, the green get a totally different schedule, and the blue get a third. And they meticulously tailored this order of operations so that if a hook error does happen, the resulting shortcut is mathematically guaranteed to be pointing in a benign direction for that specific color's local environment.
That is just breathtakingly elegant. I mean, you aren't physically eliminating the errors, you're just organizing the timeline so the errors point themselves into a corner where they can't do any harm.
Exactly. And importantly, they achieved this context-aware scheduling without sacrificing the raw speed of the system.
Right, because that was the other concern.
Yeah. This new color-dependent circuit still has minimal depth. They managed to interleave these three different schedules so perfectly that adjacent hexagons don't clash with each other.
That sounds like a massive logistical puzzle.
It really is. In quantum computing, we measure two types of error X errors, which are bit flips, and Z errors, which are phase flips. This new schedule allows all the X-type checking to happen in parallel across the board in exactly 6 time steps, and all the Z-type checking takes just another 6, so it remains incredibly fast.
Okay, so if they figured out how to point all these errors safely into a wall in the vast center of the grid, my immediate thought is, well, what happens when they actually hit the physical edge of that grid? Because the bulk of the system is this beautiful sea of interlocking hexagons, but a physical computer chip eventually has an edge. The geometry has to change, right?
You've hit on the exact complication. At the boundaries of the color code chip, the shapes aren't hexagons anymore, they're actually trapezoids.
Oh, right.
They only contain 4 data qubits, not 6. And because the shape changes, the local context changes.
So does the color-dependent schedule fall apart at the edges?
Yeah.
Do the shortcuts start pointing in dangerous directions again?
Not completely, but it does become slightly less perfect. The researchers found that at the boundary, no single isolated hook error reduces the distance, which is fantastic news.
I think it.
However, a highly specific combination of faults can synergize. They call it a fractional hook error.
A fractional hook error.
Yeah, if you get exactly 3 specific hook errors combined with 2 standard data errors perfectly aligned right at the physical edge of the chip, they multiply. They basically act as if a much larger string of errors had occurred.
I mean, that sounds like incredibly rare alignment.
It is rare, definitely. But a quantum computer performs billions of operations a second. So statistically, it will happen. And mathematically, it shaves a tiny bit off your defense shield.
Okay, so it does take a hit.
A small one. But here's the critical part. It is a fixed penalty based entirely on the geometry of the edge. Whether your system have 100 qubits or 1,000,000 qubits, the penalty at the edge stays roughly the same.
Oh, I see.
So as you scale the system up to become a truly useful machine, that tiny boundary quirk just becomes a drop in the ocean. It becomes mathematically negligible.
So what does this all mean when the rubber meets the road? Because, I mean, theoretical math and custom schedules are amazing, but we're trying to build real hardware here. Did they actually test this to see if it performs better than the old bloated methods?
They absolutely did. The researchers ran exhaustive Monte Carlo simulations.
Yeah.
Essentially, they simulate the quantum chip in software and then just bombard it with billions of randomized error scenarios to see exactly when and how the defense shield breaks.
All right, stress testing it.
Exactly. They ran these tests using the STIM simulator, and they paired it with a specialized software decoder called Tesseract to process the resulting errors.
And I imagine the type of simulated errors matters immensely here, right? Because real quantum hardware is super messy, and different materials produce different kinds of noise.
Crucially so. They tested their new color-dependent circuit against all the previous heavyweights. The uniform trioptimal circuit, the middle-out circuit, and that hardware-heavy super-dense circuit we talked about.
Okay.
And they tested them across different noise models. They started with basic theoretical noise, but the most important test they ran used the SI-1000 model.
Wait, what exactly is the SI-1000 model?
It stands for superconducting inspired. It's a highly rigorous, realistic noise model designed by the industry to perfectly mimic the exact types of crosstalk, leakage, and gate errors we currently see in real, cutting-edge superconducting quantum chips.
That's the gold standard.
Yeah. If you want to prove your quantum theory actually works for the engineers building the machines today, you have to beat the SI-1000 model.
And did the color-dependent schedule beat it?
Brilliantly. Under that realistic superconducting noise model, this custom scheduling just outperformed everything else.
Wow.
Yeah. In quantum computing, we measure the ultimate success of an architecture by its teraquap footprint.
Teraquap footprint.
Right. That is the total number of physical bits you need to reliably perform 1 trillion quantum operations without a single logical error.
Okay.
And when they ran the numbers, the teraquap footprint required by this new color-dependent circuit is roughly 20% smaller than the next best option.
Wait, a 20% reduction in hardware for the exact same processing power?
Yes.
That is massive. We aren't talking about shaving off a few dozen qubits. If you're a company trying to build a commercial system that requires millions of physical qubits, a 20% reduction means saving hundreds of thousands of microscopic, supercooled components.
It's huge.
I mean, it could shave years and hundreds of millions of dollars off the development timeline.
It entirely changes the economic and practical calculus of building a color-coded quantum computer.
Synthesizing all of this for you listening, if you care about the timeline for when we'll actually have useful, fault-tolerant quantum computing, whether your goal is to, discover new pharmaceuticals, perfectly model climate change, or crack new encryption methods, this paper is a massive, tangible win.
Absolutely.
It proves that our first instinct to solve a bottleneck shouldn't always be the bulldozer. We don't always need to build bigger, more expensive, more resource-intensive hardware arrays just to achieve fault tolerance. Sometimes the hardware we have is perfectly fine. We just need to be much, much smarter about the choreography. We need to stop treating every neighborhood like it has the exact same traffic flow.
If we connect this to the bigger picture, it really highlights a fascinating contrast in how we approach problems. In the surface code, when researchers face bad schedules that create similar hook errors, they have an easy out.
Oh, they do?
Yeah, they use the space-time trick. They basically just run the schedule forward in one round and backward in the next round. It effectively cancels out the errors in time.
Oh, they just throw the schedule in reverse.
Exactly. But that simple trick fundamentally does not work for the color code, just because of how its specific measurements are separated. The color code literally forced Kishony and Fowler to find a purely spatial solution.
Right.
They had to actually look at the physical map of their system and realize that the red, green, and blue zones each demanded their own unique rules. It forced a deeper engagement with the system's actual context.
And I think that raises an important question for you to mull over today. Whether you work in quantum physics, logistics, software development, or even management, think about the stubborn bottlenecks in your own world. How many of those problems are you currently trying to solve with blunt force hardware?
Yeah, throwing money at the problem.
Right. Are you buying more servers, expanding your budget, or hiring more staff when a hyper-localized, context-aware schedule might completely eliminate the friction you're experiencing?
Sometimes the absolute best upgrade you can make isn't physical at all.
Exactly. Is the difference between building a wider highway and finally realizing you just need to time the traffic lights to match the actual flow of the cars. Well, thank you so much for joining us on this deep dive. We hope it gives you a new lens for the complex systems around you. Keep questioning, keep exploring the hows and whys of the information you consume, and we will catch you on the next one.